All right, let's jump right into this explainer and demystify that exact moment in math class when numbers suddenly and kind of rudely turn into letters. If you've ever stared at a math problem and wondered why on earth the alphabet was invading your arithmetic, trust me, you are definitely not alone. Today, we're going to unpack exactly how variables work in equations. We'll turn what looks like a chaotic jumble of characters into a totally logical, incredibly powerful tool for solving problems.
Here's our roadmap for today. We'll hit 1. Why letters in math. 2. Anatomy of an equation. 3. The variable's dual identity. 4. Common algebra misconceptions. And finally, 5. Variables in the real world. Let's get into it.
Starting off with Section 1. Why letters in math. The origin of the variable.
So, I'm sure you've asked yourself at some point, why do we have to use all these letters, and why is X almost always the star of the show? I mean, it feels completely arbitrary, doesn't it? Well, it turns out the answer actually stems from a fascinating linguistic translation workaround from centuries ago.
What's really wild here is that the letter X literally started as a substitute for the word something. As Terry Moore points out in Cosmos magazine, a huge chunk of our mathematical foundation came directly from Arabic texts. The Arabic word for an unknown quantity was shay'un, but when Spanish scholars were translating this, they hit a major roadblock. The Spanish language doesn't have a sh sound. So their workaround? They just borrowed the Greek letter chi, which happens to look exactly like our modern X.
This whole historical journey is pretty amazing. It starts way back in 1500 BC with ancient Egyptian aha problems, where aha literally meant stack or quantity. Then we jump to the Arabic shay'un and into that Spanish translation workaround around 1200 AD. But the standard convention we use today, that didn't happen until the 1600s, thanks to French mathematician René Descartes. He's the guy who decided we should use the beginning of the alphabet, like A, B, and C for known parameters, and the end of the alphabet, X, Y, and Z for our unknowns.
Okay, moving right along to Section 2, Anatomy of an Equation, the building blocks of algebra.
So the absolutely crucial thing to grasp here is the difference between an expression and an equation. An expression is really just a phrase. Think of something like 5x minus 17. There's no equal sign. It has a value, sure, but that value changes depending on what x is. But the second you drop an equal sign in there, making it 5x minus 17 equals 18, boom, you have an equation. It's now a complete mathematical sentence. It's making a definitive statement that whatever is on the left side is perfectly balanced, just like a physical scale, with whatever is on the right side.
Now, when you see a fixed constant number attached directly to a variable, we call that a coefficient. Take a look at the 3 in 3x. That 3 is your coefficient. It's basically telling you exactly how many of that variable you have. So if x represents a box of apples, the 3 is just saying, hey, you have 3 boxes. It's also super important to remember that terms are only separated by addition and subtraction signs. You can think of those plus and minus signs as structural boundaries or actual walls in your math sentence. Multiplication and division, they act like cohesive glue, binding numbers and letters together into a single unit. So something like 8xyz is literally just one single term because it's all glued together by multiplication. But the moment you drop a plus or minus sign in there, you've built a wall and started a brand new term.
Before we move on, take a quick look at how we directly translate everyday English phrases into these algebraic terms. Algebra is quite literally its own language. So when you read the sum of x and 5, you just write x plus 5. Decrease by 2 simply becomes your variable minus 2. Honestly, mastering algebra really just starts with learning how to translate normal English sentences into mathematical ones.
Right, let's jump to Section 3, the variable's dual identity. One symbol, two meanings.
This is a hidden tension that trips up so many people. A variable actually has a dual identity. It can be an exact, but temporarily hidden number, or it can be a wildly varying quantity acting as a dynamic placeholder. For example, in the equation x plus 7 equals 11, x is a specific unknown. It's locked in. It literally must be 4 to keep the scale balanced. But if you just have the simple expression x plus 5, x is a varying quantity. It could be 2, it could be 10, it could be a million. Recognizing which identity x is playing is totally key to unlocking algebra.
On to Section 4, Common Algebra Misconceptions, addressing the classic pitfalls.
The first major pitfall students hit is confusing the variable x with the multiplication sign.
And honestly, this is exactly why upper-level math ditches the traditional x and switches to dots or parentheses. If you write 3 times x equals 9 using the old elementary school x for multiplication, it looks like 3x equals 9. It's complete visual chaos. So, to fix this, we use a dot, parentheses, or honestly just smush the coefficient right next to the variable to show multiplication.
Another massive misconception is trying to combine unlike terms. A classic example is looking at 5x plus 4 and thinking it equals 9x. People do this and completely forget that the x makes it a totally distinct variable term. Remember our structural boundaries from earlier? 5x is one term, 4 is a completely different term. It's literally like trying to add 5 apples and 4 baseballs and claiming you have 9 apple baseballs. It just doesn't work. You can't combine them because they aren't the same unit.
Research from the Mathematics Teaching Research Journal actually helps map out how these systemic errors form. It shows that when students transition from basic arithmetic into abstract algebra, they try to carry over their old, naive theories. They look at 5x plus 4 and want to just add the 5 and the 4 together, because, well, that's what arithmetic taught them to do. They do this by completely ignoring the new structural rules of the algebraic language.
Let's bring this all home with Section 5, Variables in the Real World, Solving the Burger Puzzle.
Okay, imagine you have exactly $13 in your pocket, and you are starving. How do we actually use variables to solve this efficiently? You're at your favorite spot. Double bacon cheeseburgers are $4. A drink is $1. You have exactly $13 to spend. How many burgers can you get? If we let x act as our wild card, representing the unknown number of double bacon cheeseburgers, we get the equation 4x plus 1 equals 13. Look at how perfectly real life translates into math here. The $4 is our coefficient. It multiplies by the number of burgers we buy. The $1 is our constant, right? Because we're only buying one drink, and the whole thing must balance out to equal the $13 we have in our pocket.
Now we just follow a simple 3-step rule to isolate our variable. First, we subtract the $1 drink constant from both sides, which leaves us with 4x equals 12. Then, we divide by our coefficient of 4. Remember, an equation is a balance scale. Whatever we do to one side, we literally have to do to the other. By taking away the $1 drink from both sides, we clearly see we have $12 left just for burgers. Divide that $12 by the $4 cost of each burger, and we get x completely by itself.
So we find out that x equals 3, meaning you can buy exactly 3 burgers with your money. You just successfully used a variable as a placeholder for an unknown quantity, isolated it, and solved a very real-world problem.
Once you stop seeing variables as just a confusing, random jumble of letters and start seeing them as powerful placeholders for actual solutions, the whole game changes. Algebra isn't just about finding x, it's about gaining direct access to the hidden relationships in the world around you. Whether you're managing your finances, figuring out travel times, or engineering the future, the variables are out there, waiting for you to plug them in. So, what complex, real-world unknowns will you unlock today?